There's a problem that crops up from time to time through this course that's related to the theorems we were just working on. It looks like this. Let A be a fixed m by n matrix. Find all the m by 1 matrices B such that this system here, Ax equals B, is consistent. Now, the equivalent statements theorem has that if A is invertible, then this system is always consistent no matter what B you choose. So it comes down to a matter of what if this system, what if this matrix here, A, is not invertible, or what if it's not even square, right? So that's here, that doesn't necessarily have to be square. Okay? So here's an example of how we might say what B, what values of B might work here. So here's a system. It's 3 by 3, so this is actually a square one, but I have chosen it so that, as you'll see, the coefficient matrix here, A, is not invertible. But I just set up the augmented matrix and see what it takes to find a solution. Why is this spazzing out on me here? So I'm gonna, I've already got a 1 right here, so I'm gonna get zeros there, so I'm adding the appropriate things to both of those rows. And then notice that this row and that row look very much the same. And so when I do that next step, when I add row 2 to row 3, I get a whole bunch of zeros across here. Okay? Now, in order for this system to be consistent, I can't have this last line ending up looking like 0 equals 1. So I need this thing right here. In order for this to be consistent, come on now, this can only be consistent if this is true. So there's one condition that has to be met in order for this system to be consistent. You can choose any two of B1 and B2, but then the third one, we could just solve for, say, B3 here. Oops, let's actually get a pencil, not the dot. Okay. So B3 would be 7B1 minus B2. So choose B1 and B2. B3 is determined. And once you have values like that, then you have a consistent system. So if you chose, for instance, 1 and 2, so if I said B1 equals 1, B2 equals 2, then 7 minus 2 is 5. I need B3 to equal 5. And if I plug them back up here for B1, B2, and B3, then I have a system that is consistent, and I could find some solutions for x1, x2, and x3. Now, I happen to notice here that yes, it'll be consistent, but because of this line here with a bunch of zeros, and I'm forcing this one to be 0, then not only will I have one solution, but I'll have infinitely many solutions because I will have a free variable here. So this comes up from time to time, particularly when we're looking at transformations later on, but it seems to me there's one other place which is escaping me at the moment where we're looking at rank and nullity and things here that you can see certain things like you got 2 degrees of freedoms on the B, but you only have 1 degree of freedom in your solution space. But notice 2 plus 1 is 3, and this was a 3 by 3 system. And anyway, there's a lot of things that we'll be able to say about this as we move through the quarter.